Tonight, we are going to follow the universe all the way to its end, not to a dramatic collapse or a sudden catastrophe, but to something quieter and in many ways more profound. A slow, patient dimming of everything that has ever produced light. The stars will go out one by one. The galaxies will fall silent, and what remains will be cold, dark, and still beyond anything the human mind was built to imagine. Welcome to Sleepy Time Universe, where the biggest questions in science are explored at the pace of a calm and restful night. We will begin where we are, in a universe that is still alive with light, still forming stars, still expanding outward in every direction. And we will move slowly through time, through the eras that astronomers have mapped out across scales so large that our familiar units of years and centuries become meaningless. Along the way, we will look at what stars actually are, how they spend their fuel, and what they leave behind. We will consider the fate of galaxies, the slow decay of matter itself, and the deepest, quietest era of all. A time so far in the future that the present moment would seem almost incomprehensibly brief by comparison. There is no rush tonight. The universe has plenty of time, and so do we. Let's begin. Chapter 1. A universe still burning. To understand where the universe is going, it helps to appreciate where it stands right now. We live in what cosmologists sometimes call the Stelliferous Era, the age of stars. It began a few 100 million years after the Big Bang, when the first stars ignited in the darkness of an early cosmos, and it will continue for a very long time yet. By current estimates, the Stelliferous Era stretches from roughly 100 million years after the Big Bang to somewhere around 100 trillion years from now. We are approximately 13.8 billion years into that span. In the full sweep of cosmic time, we are still near the beginning, still in the opening warmth of an era that has barely found its footing. This is worth sitting with for a moment. When we look up at the night sky and see stars scattered in every direction, we are witnessing the universe during one of its most active and luminous periods. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, each one a sustained nuclear furnace converting hydrogen into helium and releasing enormous quantities of energy in the process. Across the observable universe, there are estimated to be somewhere in the range of 2 trillion galaxies, each hosting their own vast and varied populations of stars. The total amount of light being produced right now, in this present moment, is almost beyond any useful description. It is staggering in its scale, and it is everywhere at once. And yet this era is not permanent. It is not even particularly long, measured against the full timeline that physics allows. The stars are burning through a finite supply of hydrogen, and when that hydrogen is spent, no new stars will form to replace them in any meaningful number. The darkness that follows will last incomparably longer than the light that preceded it. Understanding that contrast between the brief, luminous present and the vast dark future is at the heart of what we are exploring tonight. Stars form from clouds of gas and dust, primarily hydrogen, the most abundant element in the universe. These clouds exist within galaxies, gathered in vast structures called nebulae, and under the right conditions, they begin to collapse under their own gravity. As a cloud collapses, it grows denser and hotter at its center. The process takes time, sometimes millions of years, but eventually the pressure and temperature at the core become high enough to trigger nuclear fusion. Hydrogen nuclei begin to combine, forming helium and releasing energy. At that point, a star is born. It begins to shine. It pushes outward with the pressure of that released energy, balancing the inward pull of gravity, and it settles into a stable period of sustained burning that can last millions or billions of years depending on its mass. The relationship between a star's mass and its lifespan is one of the more counterintuitive facts in all of astrophysics. You might reasonably expect that a larger star, with more fuel available, would burn for longer. But the opposite is true. Massive stars burn their fuel at an extraordinary rate, pouring out energy so intensely that they exhaust their hydrogen supply in only a few million years, living brilliantly and briefly before ending in spectacular supernova explosions. Smaller stars, by contrast, are far more economical with their reserves. A red dwarf, the most common type of star in the observable universe, burns so slowly and steadily that it can remain in its stable phase for trillions of years. Some of the smallest red dwarfs may continue fusing hydrogen for 10 trillion years or more. To put that in perspective, 10 trillion years is roughly 700 times the current age of the universe. These stars are in no hurry at all. Our own Sun sits somewhere in the middle of this range. It is a medium-sized star, approximately 4.6 billion years old, and it is expected to continue fusing hydrogen for another 5 billion years or so before its internal structure begins to change in ways that will eventually end its life as a main sequence star. For the purposes of tonight's journey through deep time, the Sun is a relatively short-lived object, a brief and warm candle compared to the patient red dwarfs that will continue their quiet burning long after it is gone and cold. The diversity of stars in the present universe is genuinely remarkable, and it speaks to the range of timescales over which the Stelliferous Era will play out. There are blue giants burning at surface temperatures of tens of thousands of degrees, consuming their fuel so rapidly that their entire lives pass in what amounts to a cosmic instant. There are yellow stars like our own, steady and reliable over timescales of billions of years, sustaining the warmth of entire planetary systems across their long and stable lives. There are orange subgiants growing slowly larger and cooler as they age, shifting in character as they exhaust the hydrogen at their cores. And there are the red dwarfs, quiet and dim, so careful in their consumption that they will outlast almost everything else in the cosmos by an enormous margin. Each of these stellar types represents a different relationship with time, a different pace of burning, a different contribution to the slow arc of the universe's total light. What all stars share, regardless of their size or temperature or color, is that they are working from a limited reserve. The hydrogen available for star formation is not being replenished in any significant way. What existed in the aftermath of the Big Bang, and what was later processed and redistributed through generations of stellar birth and death, is essentially what remains to work with. As more of that hydrogen is consumed and locked away in stellar remnants, in white dwarfs, neutron stars and black holes, less remains available to form new generations of stars. The rate of star formation across the observable universe has already been declining for billions of years. Astronomers believe it peaked somewhere around 10 billion years ago, when the universe was roughly 3 to 4 billion years old. Since then, fewer and fewer new stars have been igniting each year. We are well past the most productive era of stellar birth. This slow decline in star formation is one of the quietest and most consequential processes in all of cosmology. It is not a sudden event. It produces no flash of light, no detectable signal. It is simply a direction, a gradual shift in the balance between what is being created and what is being consumed. And the direction leads over immense and almost unimaginable stretches of time toward a sky with fewer and fewer points of light. The galaxies will not go dark all at once. They will fade, one star at a time, over trillions of years, as the available fuel is slowly spent and the conditions for new star formation become increasingly rare. There is something deeply peaceful about this picture if you allow yourself to settle into its scale. The universe is not rushing toward its end. It is not collapsing in panic or burning out in crisis. It is simply aging, slowly and thoroughly, the way all things age when given enough time. The light we see tonight is the product of conditions that have been building for nearly 14 billion years, and those conditions will continue to produce stars and light for a very long time to come. But they will not continue forever. The fuel is finite, the arc is set, and the direction, followed far enough, leads to darkness. For now, we remain in the warm middle chapter of the Stelliferous Era, surrounded by more light than we can begin to count. The stars above are burning steadily, as they have for billions of years, as they will for billions more. The universe is still young enough that its eventual fate seems almost theoretical, a conclusion so far removed from the present that it carries no weight of urgency at all. And that distance is precisely what makes it such a good companion for a quiet night. We are exploring something vast and inevitable, but unhurried. Something that will unfold across timescales so immense that even the word trillion feels inadequate. There is nowhere to rush to. The end of the light is still an extraordinarily long way away. Chapter 2. How Stars Die. Every star that has ever existed has been engaged, from the moment of its birth, in a process it cannot sustain indefinitely. The fusion of hydrogen into helium is not a cycle that replenishes itself. It is a one-way transaction, a slow and steady consumption of the most basic fuel the universe provides, and it ends when that fuel is gone. What happens after that ending depends almost entirely on how massive the star was to begin with. The death of a star is not a single kind of event. It is a range of outcomes, spread across an enormous variety of timescales and final states, and each outcome leaves behind a different kind of remnant in the fabric of the cosmos. The most common stars in the universe are also the least dramatic in their deaths. Red dwarfs, which make up somewhere around 70 to 80% of all stars in the observable universe, do not explode when they run out of fuel. They do not swell into giants or shed their outer layers in glowing clouds of gas. They simply fade. As a red dwarf exhausts its hydrogen, it gradually cools and dims, contracting slowly into a dense, cold object called a black dwarf. The process is extraordinarily slow by any standard, taking hundreds of billions to trillions of years from ignition to final darkness. In fact, the universe is not yet old enough for any red dwarf to have completed this process. Every red dwarf that has ever formed is still burning today. The black dwarfs that will eventually fill the cosmos do not yet exist. They are a future object, a remnant type that the universe has not yet had time to produce. Stars closer in size to our Sun follow a different and somewhat more eventful path. As a sun-like star exhausts the hydrogen in its core, the core begins to contract under gravity, while the outer layers of the star expand outward and cool. The star becomes what is known as a red giant, dramatically larger than it was during its main sequence life, with a surface temperature lower than before, but a total luminosity that can be many times greater due to its enormous size. Our own Sun will reach this stage in approximately 5 billion years, expanding to a radius that may reach somewhere near the orbit of the Earth, though the precise extent of that expansion remains a matter of ongoing study and calculation. The red giant phase does not last as long as the main sequence phase. Once the core has contracted sufficiently and temperatures have risen high enough, a new kind of fusion begins. Helium fusing into carbon and oxygen. This provides a second, shorter lease of energy, but it too is finite. When the helium is spent, a sun-like star lacks the mass needed to compress its core further and ignite the next stage of fusion. Instead, the outer layers of the star drift away into space, forming an expanding shell of glowing gas called a planetary nebula. The name is somewhat misleading. Planetary nebulae have nothing to do with planets. They were named by early astronomers who found their rounded shapes vaguely reminiscent of planets when viewed through small telescopes. What they actually are is the dispersed outer atmosphere of a dying star, lit from within by the hot core it has left behind. That core, the remaining dense kernel of the star after its outer layers have been shed, is what we call a white dwarf. A white dwarf is roughly the mass of the Sun compressed into a volume comparable to the Earth. It is extraordinarily dense, and it glows not from fusion, but from the residual heat it accumulated during its life. There is no new energy being generated inside a white dwarf. It is simply cooling, very slowly, radiating its stored heat into the surrounding space. Given enough time, and we are talking about timescales of many billions to trillions of years, a white dwarf will cool completely, fading from white to yellow to orange to red, and eventually going dark altogether. At that point, it becomes like the eventual fate of red dwarfs, a black dwarf, a cold, dense, inert remnant floating in the darkness with no light of its own. The most massive stars in the universe take a far more violent route to their end. Stars with masses many times greater than the Sun burn through their fuel with extraordinary speed and intensity, and when they exhaust their supply of fusible material, the result is catastrophic. The core collapses in a fraction of a second, and the outer layers of the star rebound off the collapsing core in a titanic explosion known as a supernova. For a brief period, a supernova can outshine an entire galaxy, hundreds of billions of stars, all by itself. It releases in those few weeks as much energy as the Sun will emit across its entire 10 billion year lifetime. It is among the most energetic events the universe produces. What remains after a supernova depends on the mass of the original star. If the core that remains after the explosion is below a certain threshold, it collapses into a neutron star, an object of almost incomprehensible density, roughly the mass of the Sun compressed into a sphere perhaps 20 kilometers across. A neutron star is so dense that a single teaspoon of its material would weigh billions of tons on Earth. Neutron stars do not fuse elements and do not generate new energy. Like white dwarfs, they cool over time, though their cooling process operates on different timescales and involves different physics. If the remaining core is massive enough, even the resistance of neutron pressure cannot halt the collapse, and the result is a black hole, a region of space-time where gravity is so extreme that nothing, not even light, can escape once it has passed within the boundary, known as the event horizon. Black holes do not shine. They do not emit light. They are defined by their absence of light, by the darkness they impose on the space around them. They are, in a sense, the most complete expression of the darkness that the universe is slowly moving toward. Regions where the ordinary relationship between matter and light has been permanently severed. Supernovae are not only destructive, they are also among the most creative events in the universe. The explosion disperses into space all the heavy elements that were forged inside the star during its lifetime. Carbon, oxygen, nitrogen, silicon, iron, and many others, along with elements created in the explosion itself. These elements enrich the gas clouds from which future generations of stars and planets will form. Every atom of carbon in every living thing on Earth was forged inside a star that died before our sun was born. The deaths of stars are, in this sense, part of the process by which the universe builds complexity. But that process, too, is finite. As the available hydrogen is consumed and fewer new stars are born, the enrichment of the interstellar medium slows. The cycle of stellar birth, life, and death that has been running for nearly 14 billion years will gradually wind down, not with a single ending, but with a long and patient diminishment. What the deaths of stars leave behind, then, is a growing population of cold and silent remnants, white dwarfs cooling in the dark, neutron stars spinning down over billions of years, black holes drifting through the voids between galaxies, and eventually, when the last red dwarfs have also faded, black dwarfs joining that silent population in their countless billions. The universe of the far future will not be empty. It will be full of objects, full of matter. But it will be a universe in which almost none of that matter is doing anything that produces light. It will be a universe of remnants, patient and cold, carrying the memory of the stars in their structure without any longer expressing it in light. This transformation from a universe of burning stars to a universe of cold remnants is not a sudden shift. It is a process measured in trillions of years, unfolding so gradually that no single moment would feel like a transition. The last star will not announce itself. It will simply be the final one, burning quietly in an otherwise dark sky, and when it fades, it will do so without ceremony, leaving behind only the cold remnant at its heart and the darkness it was holding back. The universe will not notice. There will be no one left to notice. There will only be the dark and the slow cooling of everything that remains. Chapter 3. The Fate of Galaxies. Stars do not exist in isolation. They are gathered into galaxies, vast, gravitationally bound collections of stars, gas, dust, and dark matter that represent the large-scale structure of the visible universe. The Milky Way, our own galaxy, contains hundreds of billions of stars arranged in a flattened spiral disk with a dense central bulge, all held together by gravity and dark matter in a structure roughly 100,000 light-years across. It is an enormous object by any human standard, and yet it is only one of an estimated 2 trillion galaxies in the observable universe, each one a city of stars embedded in the larger architecture of cosmic structure. The fate of these galaxies is inseparable from the fate of the stars within them. As star formation slows and the stellar population ages, galaxies themselves undergo a transformation. They do not remain the bright, active, star-forming structures we observe today. They evolve, they merge, they fade, and over timescales that dwarf even the long lives of red dwarf stars, they become something almost unrecognizable from their luminous origins. To understand how the universe ends in darkness, we need to understand what happens to galaxies across deep time, how they change, what forces act upon them, and what they eventually become. The story of galaxies across cosmic time begins with their formation, which is itself a process intimately tied to the distribution of dark matter in the early universe. Dark matter, which does not emit or absorb light, but does exert gravitational influence, formed large-scale structures called halos in the early universe, and ordinary matter, hydrogen and helium gas, fell into these halos and condensed into the first galaxies. Over billions of years, galaxies grew by accumulating gas from their surroundings and by merging with other galaxies. The history of the universe is in large part a history of galactic mergers, smaller structures combining into larger ones, pools of stars and gas flowing together under gravity to form the massive galaxies we observe today. Our own Milky Way is currently on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor, located approximately 2.5 million light-years away. The two galaxies are approaching each other at several hundred kilometers per second, and astronomers estimate that they will begin to interact in roughly 4 to 5 billion years. The merger will unfold over billions of years, a slow gravitational dance in which the two galaxies pass through each other, distort each other's structure, and eventually settle into a single larger elliptical galaxy. This future object is sometimes informally referred to as Milkomeda, a combined structure that will contain the stars of both original galaxies, reorganized by the forces of the merger into a new and different form. It is important to note that galactic mergers, despite their dramatic description, are not catastrophic for individual stars. The distances between stars within a galaxy are so vast that direct stellar collisions during a merger are extremely rare. What changes is the distribution and orbits of stars, the triggering of new bursts of star formation as gas clouds are compressed by the merger dynamics, and the overall shape and structure of the resulting galaxy. Mergers can temporarily increase the rate of star formation, burning through available gas more quickly and accelerating the long-term decline in stellar activity. In this sense, the merger of the Milky Way and Andromeda, while spectacular, will also hasten the eventual fading of the combined galaxy by consuming star-forming material at an elevated rate. Beyond our local group of galaxies, the large-scale structure of the universe is shaped by dark energy, a mysterious component of the cosmos that is causing the expansion of the universe to accelerate. As the universe expands at an accelerating rate, galaxies that are not gravitationally bound to each other are moving apart faster and faster. Over billions of years, the galaxies that currently populate our observable universe will recede beyond the cosmological horizon, the boundary beyond which light can no longer reach us because the space between us and those galaxies is expanding faster than light can travel across it. This does not mean those galaxies cease to exist. It means they become permanently unreachable and unobservable from our location. The observable universe will gradually empty of the distant galaxies we can currently see, leaving only our local group of gravitationally bound galaxies visible against an otherwise dark sky. This process is already underway. The most distant galaxies we can currently observe are receding from us at speeds that exceed the speed of light due to the expansion of space itself, and over time, the number of galaxies within our observable horizon will decrease. The universe will not become less populated in an absolute sense, but it will become lonelier from any given vantage point. The great tapestry of galaxies that fills our current night sky, visible in long exposure images as an almost uncountable scatter of luminous islands, will, given enough time, shrink to a single merged local group surrounded by an empty dark. Within the local group itself, and within merged galactic structures like Milkomeda, the stars will continue their slow aging. The most massive stars will have long since exhausted their fuel and left behind their remnants. Medium-sized stars like the Sun will have completed their journey through the red giant phase and settled into white dwarfs, cooling over billions of years. The red dwarfs, still burning their fuel with patient economy, will remain the last active stars, dim, cool, and extraordinarily long-lived, continuing to shine in the merged galaxy long after every other stellar type has gone dark. As the available gas for star formation is consumed and not replenished, the rate of new star formation within these galactic structures will decline towards zero. Galaxies will transition from active star-forming systems to what astronomers call quenched galaxies, structures in which star formation has effectively ceased. We can already observe this process in the universe today. Many large elliptical galaxies, particularly those in dense galaxy clusters, have already exhausted their star-forming gas and are populated almost entirely by old, cool stars. They are, in a sense, a preview of what all galaxies will eventually become. Aging populations of stars slowly cooling and fading, no longer producing the blue and white brilliance of young stellar populations, settling instead into the dim red glow of old age. The structure of galaxies will also be affected over deep time by gravitational interactions between stars themselves. In any gravitationally bound system, interactions between members of the system will gradually redistribute energy. Some stars will gain energy through these interactions and be ejected from the galaxy entirely, escaping into the intergalactic void on trajectories that will carry them away forever. Other stars will lose energy and sink toward the center of the galactic structure. Over timescales of perhaps 10 to the power of 19 to 10 to the power of 20 years, numbers so large that they require exponential notation to express conveniently. This process of gravitational relaxation will cause most of the stars in a galaxy to either escape into the void or fall toward the central region. The galaxy as a coherent structure will gradually dissolve, not through any dramatic event, but through the slow statistical outcome of countless gravitational nudges accumulated over an almost incomprehensible span of time. At the centers of most large galaxies, including our own Milky Way, there are supermassive black holes. The Milky Way's central black hole, known as Sagittarius A star, has a mass of approximately 4 million times that of the Sun. Andromeda's central black hole is considerably more massive. When the two galaxies merge, their central black holes will eventually merge as well, forming an even more massive black hole at the heart of Milkomeda. As the surrounding stars are gradually ejected or consumed over deep time, these central black holes will become the dominant remaining structures in what were once magnificent spiral galaxies. The stars that built those galaxies, that illuminated them for trillions of years, will be gone, escaped into the void or swallowed into darkness. And what remains will be the black holes at their hearts, patient and dark, holding the gravitational memory of the galaxies that once surrounded them. There is something quietly moving about this picture of galactic fate. The galaxies we observe today, with their sweeping spiral arms, their glowing cores, their vast populations of stars in every stage of life, are not permanent features of the universe. They are structures of a particular era, products of conditions that allowed gas to cool and condense and ignite into stars on a vast scale. That era is already past its peak. The galaxies around us are aging, their star-forming days gradually behind them, their futures stretching out into a long and patient dimming. They will not vanish suddenly. They will simply grow quieter and darker and stiller, over timescales so vast that the difference between 1 billion years and 1 trillion years becomes difficult to hold in the mind. And in that stillness, the universe will continue its patient expansion, carrying the remnants of its galaxies further and further apart, into a darkness that has no end in sight. Chapter 4. The Long Twilight of Red Dwarfs. When the massive stars are gone and the medium stars have faded into white dwarfs, the universe will still have light. It will not be the brilliant, varied light of the present era, the blue-white blaze of young giants, the warm yellow glow of sun-like stars, the rich tapestry of stellar colors that fills the night sky today. It will be something quieter and more uniform. The last fires of the Stelliferous Era will be red, dim, cool, patient points of light scattered through the darkness of aging galaxies, burning so slowly and so carefully that they will outlast everything else the universe has produced by an almost incomprehensible margin. These are the red dwarfs, and their story is one of the longest single chapters in the history of the cosmos. Red dwarfs are the most common stars in the universe. Estimates suggest they account for somewhere between 70 and 80% of all stars in the Milky Way, and a similar proportion likely holds across other galaxies. They are small, typically between about 8% and 50% of the mass of the Sun, and they burn at surface temperatures cool enough to give them their distinctive reddish hue. They are not dramatic objects. They do not blaze with the intensity of blue giants or warm planetary systems, with the comfortable reliability of sun-like stars. They are modest, quiet, and extraordinarily long-lived, and it is precisely those qualities that make them the last light the universe will know. The longevity of red dwarfs comes from two related properties. The first is their low mass, which means they have less fuel to burn, but also require far less energy output to maintain the balance between gravity and radiation pressure that keeps a star stable. The second is the way they manage that fuel. Unlike larger stars, which develop distinct layers with different compositions as fusion progresses, a hydrogen-burning shell surrounding a helium core, for instance, red dwarfs are fully convective. This means that the material inside them is continuously circulated throughout the entire star, like a slowly stirred pot. As hydrogen in the core is consumed, fresh hydrogen from the outer layers is mixed back in to replace it. A red dwarf does not run out of fuel at its center while still carrying reserves in its outer layers. It has access to nearly all of its hydrogen supply throughout its life, and it uses that supply with extraordinary efficiency. The result is a lifespan that is almost beyond meaningful comparison with human experience. A red dwarf at the lower end of the mass range, say a star with about 8% of the Sun's mass, just barely massive enough to sustain fusion, may burn for somewhere in the region of 10 trillion years. That is 10,000 billion years compared to the current age of the universe of 13.8 billion years. Such a star, if it formed in the early universe, would today be less than 1/10 of 1% of the way through its life. It has barely begun. The universe, from the perspective of that star, is still in its infancy. This extraordinary longevity means that red dwarfs will dominate the stellar population of the universe for an almost incomprehensible span of time. As the more massive and medium stars complete their life cycles and leave behind their remnants, the red dwarfs will continue burning, unchanged in any meaningful way, long after the last sun-like star has cooled to a white dwarf. The galaxies of the far future will not be dark. They will be dim, populated by these small, cool, patient stars glowing faintly in the red portion of the spectrum, providing a kind of extended twilight to the universe long after its more brilliant phase has ended. Life around a red dwarf, if it exists anywhere in the universe, would experience a very different kind of stellar environment from what we know on Earth. Red dwarfs are prone to powerful flares, sudden releases of magnetic energy that can briefly increase the star's output dramatically. Any planet close enough to a red dwarf to be in its habitable zone, where liquid water might exist on the surface, would be exposed to intense radiation during these flares. The habitable zones around red dwarfs are also much closer to the star than Earth is to the Sun, which means planets in those zones are likely to be tidally locked. one hemisphere permanently facing the star in endless day, the other in endless night. The conditions are different from Earth in almost every respect, and yet the sheer number and longevity of red dwarfs means that if life can adapt to those conditions, it would have trillions of years in which to do so. But the red dwarf era, long as it is, also has an end. As a red dwarf exhausts the last of its hydrogen, it does not have the mass to compress its core and begin fusing helium. There is no red giant phase, no planetary nebula, no dramatic finale. The star simply fades. It cools progressively, its surface temperature dropping, its color shifting from red toward infrared as the energy output declines. Eventually, it passes below the threshold at which it can sustain fusion at all, and the light goes out. What remains is a black dwarf, a cold, dense ball of helium and unburned hydrogen, roughly the size of a large planet, but with the mass of a small star, drifting silently through the dark. As noted earlier, no black dwarfs yet exist in the universe. The cooling process takes longer than the current age of the cosmos. But as the trillions of years of the red dwarf era pass, they will form in increasing numbers, each one the cold remnant of a star that burned longer than almost anything else the universe produced. By the time the last red dwarf has faded, somewhere around 10 trillion years from now, give or take the variations across the range of red dwarf masses, the universe will have accumulated an enormous population of these dark remnants, along with the white dwarfs and neutron stars and black holes left behind by earlier stellar generations. The Stelliferous Era will be over. The age of stars will have ended not with a catastrophe, but with a slow, patient extinction of the last dim lights, one by one, across trillions of years. There is a particular quality to the image of the last red dwarfs burning in an otherwise dark universe. By that point in cosmic history, the sky around any of those stars would look nothing like the sky we know. The brilliant galaxies of the present universe would be long gone from view, receded beyond the cosmological horizon by the accelerating expansion of space. The merged remnants of local galactic structures would be populated almost entirely by cold, dark objects, black dwarfs, neutron stars, black holes, with only the remaining red dwarfs providing any light at all. A hypothetical observer in that era would look out into a universe that appeared almost completely dark, with only scattered dim red points of light marking where the last stars continued their patient burning. And then, one by one, those lights would fade. Not dramatically, not suddenly, but gradually and completely, each star cooling through its final stages over billions of years, its glow shifting from visible red to infrared to nothing detectable at all. The last star to go dark will not be a notable event in any cosmic sense. There will be no observer to mark it. There will be no sound, no flash, no signal of any kind. There will simply be a universe that contained one last burning star, and then a universe that did not. The transition will be as quiet as everything else in the long twilight of the red dwarf era. Patient, complete, and absolute. What follows that ending is something different entirely. A universe without stars is not simply a darker version of the universe we know. It is a fundamentally different kind of place, governed by different processes, operating on timescales that make even the lifespan of a red dwarf seem brief. The Stelliferous Era will have given way to what comes after, and what comes after has its own long and quiet story to tell. Chapter 5. The Degenerate Era. When the last red dwarf has cooled and the Stelliferous Era has finally closed, the universe will enter a phase that cosmologists call the Degenerate Era. The name comes not from any sense of moral decline, but from the physics of the objects that will dominate this period. Degenerate matter, a state in which the behavior of particles is governed not by heat and pressure in the conventional sense, but by quantum mechanical effects that resist compression, even in the absence of any ongoing nuclear reactions. The objects of the degenerate era are the remnants left behind by stellar evolution: white dwarfs, neutron stars, and black holes. And they will populate the universe in vast numbers, drifting through the dark in a cosmos that no longer produces any significant light of its own. The degenerate era is estimated to span from roughly 10 trillion years after the Big Bang, when the last red dwarfs are fading, to somewhere around 10 to the power of 40 years from now. That upper boundary is so far beyond ordinary numerical intuition that it is worth pausing to appreciate its scale. 10 to the power of 40 is a 1 followed by 40 zeros. The current age of the universe, 13.8 billion years, is roughly 10 to the power of 10. The degenerate era therefore spans a length of time approximately 10 billion times longer than the current age of the universe. It is not merely a long period. It is a duration that makes everything that has come before it seem like a brief prologue. During this immense span of time, the universe will be a very different kind of place from anything we can observe today. There will be no stars burning, no nebulae glowing, no active galaxies pouring light into the surrounding space. The primary inhabitants of the cosmos will be white dwarfs, the cooling remnants of medium-sized stars, along with neutron stars, black holes, and the cold black dwarfs that were once red dwarfs. These objects will continue to drift through the remnants of what were once galaxies, their orbits slowly evolving under the influence of gravitational interactions, their surfaces cooling toward the ambient temperature of the universe. White dwarfs will be among the most numerous objects in the degenerate era. A white dwarf is supported against gravitational collapse not by the pressure of ongoing fusion, but by a quantum mechanical effect called electron degeneracy pressure. Electrons, as fermions, obey a principle that prevents two of them from occupying the same quantum state simultaneously. When matter is compressed to the densities found in a white dwarf, this exclusion principle generates a pressure that resists further compression, independent of temperature. This means that a white dwarf does not need to be hot to hold itself up. It can cool indefinitely while maintaining its structure, slowly releasing its stored thermal energy into the surrounding space over billions and then trillions of years. The cooling of white dwarfs is an extraordinarily slow process. A newly formed white dwarf has a surface temperature of tens of thousands of degrees and glows with a blue-white light. Over billions of years, it cools through white to yellow to orange to red, its luminosity declining steadily as it loses heat to the surrounding space. The universe is not yet old enough for any white dwarf to have cooled to the point of becoming a true black dwarf, completely dark and cold. But in the degenerate era, this process will have run to completion for the oldest white dwarfs, and new black dwarfs will continue to form as younger white dwarfs complete their cooling. By the middle and later stages of the degenerate era, the universe will be populated by an enormous number of these cold, dark, planet-sized remnants of former stars, each one carrying in its composition the record of the nuclear processes that created it. Neutron stars, the remnants of more massive stellar explosions, will also drift through the degenerate era in large numbers. Like white dwarfs, they are supported by a form of degeneracy pressure. In their case, neutron degeneracy pressure, which operates at far higher densities. Neutron stars cool more quickly than white dwarfs in relative terms, but they too will eventually approach the ambient temperature of the surrounding universe over the immense timescales of the Degenerate Era. Young neutron stars are detectable as pulsars, rapidly rotating objects that emit beams of radio waves as they spin. But over time, their rotation slows as they lose energy, and they become quieter and dimmer, eventually fading into cold, dark remnants indistinguishable in their silence from the black dwarfs around them. One of the most significant processes of the Degenerate Era may be something that has never yet been directly observed, but is predicted by certain extensions of the standard model of particle physics: the decay of protons. Protons are the positively charged particles at the heart of atomic nuclei, and in ordinary experience they appear to be completely stable. But some theoretical frameworks suggest that protons are not truly stable over infinite timescales, and that given enough time, a proton will spontaneously decay into lighter particles. The predicted timescale for this process varies depending on the theoretical model, but some estimates place the proton lifetime at around 10 to the power of 34 years or longer. If proton decay occurs on any timescale within the Degenerate Era, it would have profound consequences for the white dwarfs and black dwarfs that populate this period. The decay of protons within these objects would release small amounts of energy, causing them to glow very faintly, not from fusion or stored heat, but from the slow disintegration of their own atomic nuclei. Over the immense timescales of the Degenerate Era, this process would gradually erode the matter in white dwarfs and black dwarfs, converting it into lighter particles and radiation, and leaving behind, eventually, nothing but the black holes at the centers of former galaxies and whatever particles the decaying matter produced. It is worth noting that proton decay has not been experimentally confirmed. Physicists have searched for it with large underground detectors filled with water or other materials, watching for the rare flash of light that would indicate a proton decaying within the detector volume. So far, no confirmed proton decay event has been observed, which places lower bounds on the proton lifetime, but does not rule out decay on longer timescales. The question of whether protons ultimately decay remains one of the open questions of fundamental physics, and its answer has significant implications for the very long-term fate of matter in the universe. Whether or not proton decay occurs, the Degenerate Era will eventually give way to a period dominated by black holes. If proton decay does occur within the estimated timescales, the white dwarfs and black dwarfs will gradually dissolve, leaving black holes as the last surviving massive objects. If proton decay does not occur, the same outcome will eventually be reached through other means. Gravitational interactions will cause most of the stellar remnants to either escape their galactic structures entirely or fall toward the central black holes, and the black holes will grow slowly and patiently as matter is added to them over incomprehensible timescales. Either way, the endpoint of the Degenerate Era is a universe in which black holes are the dominant remaining structures, surrounded by whatever particles and radiation the decay or dispersal of ordinary matter has produced. The Degenerate Era is, in its way, a period of profound quiet. There are no explosions, no bursts of light, no active processes of the kind that characterize the universe we know. There is only the slow cooling of ancient remnants, the patient drift of dark objects through an expanding space, and the gradual operation of quantum processes so slow that they are invisible on any timescale shorter than the age of many universes. It is a period defined not by what is happening, but by what is no longer happening. A universe that has finished its age of stars and settled into a long, cold, dark patience. waiting for the next slow transformation that time and physics will bring. Chapter 6: The Age of Black Holes. When the last white dwarfs have cooled and the last neutron stars have faded into silence, when the slow processes of the Degenerate Era have run their course across timescales that dwarf even the long patience of the Red Dwarf Era, the universe will enter what cosmologists call the Black Hole Era. It is a period in which the dominant structures in the cosmos are no longer stars or their remnants, but the black holes that formed from the deaths of the most massive stars and grew over unimaginable spans of time by consuming whatever matter drifted within their gravitational reach. The Black Hole Era is not a brief transition. It is an epoch of extraordinary duration, stretching from roughly 10 to the power of 40 years after the Big Bang, to somewhere around 10 to the power of 100 years. A span so vast that the entire preceding history of the universe, from the Big Bang through the Stelliferous Era and the Degenerate Era combined, would represent an utterly negligible fraction of it. Black holes are among the most extreme objects the universe produces. They form when matter is compressed beyond a critical density, creating a region of space-time from which nothing can escape. The boundary of this region is the event horizon, not a physical surface, but a point of no return, a threshold beyond which the escape velocity exceeds the speed of light. Inside the event horizon, the ordinary rules of cause and effect as we experience them break down in ways that our current understanding of physics cannot fully describe. Outside the event horizon, a black hole makes its presence known through its gravitational influence, bending the paths of light and matter, drawing in anything that passes close enough, growing slowly as it accumulates mass. The black holes that will dominate the Black Hole Era come in a range of sizes. Stellar mass black holes, formed from the collapse of individual massive stars, have masses ranging from a few times the mass of the Sun to perhaps a few tens of solar masses. Intermediate mass black holes, formed through the mergers of smaller black holes or through other processes, occupy a middle range. And supermassive black holes, which sit at the centers of galaxies and have masses ranging from millions to billions of times the mass of the Sun, are the largest individual objects in the universe. The supermassive black hole at the center of the Milky Way has a mass of approximately 4 million solar masses. The largest known supermassive black holes have masses of tens of billions of solar masses. These enormous objects will be the last survivors of the Black Hole Era, persisting long after their smaller counterparts have gone. During the Black Hole Era, the universe will be extraordinarily dark and cold. The cosmic microwave background radiation, the faint afterglow of the Big Bang that currently permeates all of space at a temperature of about 2.7 degrees above absolute zero, will have cooled to an almost undetectable whisper by this point, redshifted by the continuing expansion of the universe to temperatures so close to absolute zero that the difference is essentially philosophical. There will be no starlight, no galaxy glow, no nebulae, no active processes of any kind producing electromagnetic radiation in significant quantities. The universe will be, to any meaningful approximation, completely dark. And yet, something will be happening. Something slow, subtle, and profoundly important. A process predicted by the physicist Stephen Hawking in 1974 that connects quantum mechanics to the physics of black holes in a way that has extraordinary long-term consequences. This process is known as Hawking radiation, and it means that black holes are not truly permanent. They evaporate. The mechanism behind Hawking radiation involves quantum fluctuations at the event horizon of a black hole. In quantum field theory, Empty space is not truly empty. It is filled with a constant ferment of virtual particle pairs, particles and their antiparticles that spontaneously appear and annihilate each other on timescales too short to directly observe. Near the event horizon of a black hole, it is possible for one member of such a pair to fall inside the horizon, while the other escapes into the surrounding space. When this happens, the escaping particle carries away a small amount of energy, and by the conservation of energy, that energy must ultimately come from the black hole itself. The black hole loses mass. Very slowly, over an extraordinarily long period of time, this process causes the black hole to shrink. The rate of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes radiate more intensely and evaporate more quickly, while larger black holes radiate so faintly that the process is almost incomprehensibly slow. A stellar mass black hole with a mass of 10 solar masses would take approximately 2 times 10 to the power of 71 years to evaporate completely through Hawking radiation. A supermassive black hole with a mass of 1 billion solar masses would take on the order of 2 times 10 to the power of 99 years. These are the timescales of the black hole era, numbers so large that they require a different relationship with the concept of duration than anything in ordinary experience provides. As a black hole evaporates through Hawking radiation, it does not simply shrink uniformly and quietly to nothing. In its final stages, as its mass decreases and the rate of radiation increases, the process accelerates. The last moments of a black hole's evaporation are relatively rapid. A final burst of radiation, as the remaining mass is converted to energy in a brief and energetic conclusion. This final evaporation releases the last of the black hole's mass energy as a spray of particles and radiation, contributing a tiny, fleeting flash of energy to the surrounding darkness before leaving nothing behind. Nothing that is, except empty space and whatever information about the black hole's contents is encoded in the outgoing radiation. A question that remains one of the deepest unresolved problems in theoretical physics, known as the black hole information paradox. The black hole era will see black holes of all sizes completing this evaporation process at different times. The smallest black holes will go first, their evaporation completing relatively early in the era. Intermediate mass black holes will follow over the middle epochs, and the supermassive black holes at the centers of former galaxies will be the last to go, persisting for the full span of the era before their final evaporation in bursts of radiation that briefly illuminate a universe that has otherwise been dark for longer than any timescale the mind can comfortably form. There is something remarkable about Hawking radiation as a cosmic process. It is, in a sense, the universe's final mechanism for converting the mass locked up in its most extreme objects back into energy and radiation. The stars converted hydrogen into helium and heavier elements, releasing energy as light and heat. The supernovae dispersed those elements into space. The black holes gathered matter unto themselves over immense spans of time. And then, slowly and completely, they gave it all back, converting their accumulated mass into radiation through a quantum process operating at the very boundary between general relativity and quantum mechanics. It is a kind of final accounting, a slow return of everything the universe had gathered into its darkest and most extreme structures. By the end of the black hole era, when the last supermassive black holes have completed their evaporation, the universe will contain essentially no large concentrations of matter at all. What remains will be a thin, extraordinarily cold soup of particles and radiation, photons, neutrinos, electrons, positrons, and whatever other stable particles physics allows, spread through an expanding space of incomprehensible size. The structures that define the universe for the entirety of its visible history, galaxies, stars, planets, black holes, will all be gone. What remains will be as close to nothing as physics permits while still being something, and the universe will continue to expand, carrying that thin remnant further and further apart, cooling toward a final state that cosmologists describe with a phrase that captures its essential character with quiet precision: the heat death of the universe. Chapter 7: Heat Death and Maximum Entropy. There is a concept in physics that sits quietly beneath almost every process in the observable universe, shaping the direction of change in everything from the cooling of a cup of tea to the evolution of stars and galaxies across billions of years. It is called entropy, and understanding it is essential to understanding what the heat death of the universe actually means, why it is inevitable, what it describes, and why the word death, with all its finality, is perhaps the most honest word available for what physics is pointing toward. Entropy is often described informally as a measure of disorder, but that description, while useful as a starting point, does not quite capture its full significance. More precisely, entropy is a measure of the number of ways the components of a system can be arranged while still producing the same overall observable state. A system with high entropy has many possible arrangements of its components that all look the same from the outside. A system with low entropy has very few such arrangements. Its components are organized in a specific, constrained way that could only be produced by a relatively small number of configurations. The reason entropy tends to increase over time is essentially statistical. There are simply far more ways for a system to be disordered than ordered, and so random processes naturally tend to move systems toward higher entropy states. This tendency is captured in the second law of thermodynamics, which states that the total entropy of a closed system will increase over time, or at best remain constant, but will never spontaneously decrease. The universe as a whole is, to the best of our understanding, a closed system. There is nothing outside it to exchange energy or information with, and the second law of thermodynamics therefore applies to it in its entirety. The total entropy of the universe has been increasing since the Big Bang, and it will continue to increase for as long as any process is occurring anywhere within it. Every star that burns, every particle that moves, every photon that travels through space, all of these contribute to the ongoing increase in the universe's total entropy. The universe is not moving toward disorder in a haphazard way. It is moving toward the state of maximum possible entropy, the state in which no further increase is possible because everything is already as disordered as it can be. That state of maximum entropy is what physicists mean by the heat death of the universe. It is not a death by heat in the sense of extreme temperature. In fact, it is precisely the opposite. The heat death is a state of perfect thermal equilibrium, a condition in which every region of the universe is at exactly the same temperature, with no temperature differences anywhere to drive any kind of process or energy flow. Temperature differences are what allow work to be done, energy to be transferred, and processes of any kind to occur. A hot star in a cold sky represents a temperature difference that drives the radiation of energy outward, which can warm planets, drive chemical reactions, and ultimately support the complexity of living systems. When that temperature difference is gone, when everything is at the same temperature, there is nothing left to drive anything. No processes can occur. No change of any kind is possible. The universe reaches a final, permanent, and absolute stillness. The temperature at which this equilibrium will be reached is not zero. Absolute zero, the complete absence of thermal energy, cannot be reached by any real physical process. The equilibrium temperature will instead be extraordinarily close to absolute zero, but not quite there. A temperature so low that it is effectively indistinguishable from nothing by any practical measure, but technically above zero by the smallest conceivable margin. The universe will be cold beyond any useful description, filled with a vanishingly thin distribution of particles and photons, all at the same feeble temperature, expanding through a space so vast that the density of even this residual content approaches zero in any finite volume. It is worth considering what the universe will actually contain at this stage. After the evaporation of the last black holes, the primary constituents of the universe will be the stable particles that physics permits to exist indefinitely. Photons, particles of light, will be present, but redshifted by the expansion of the universe to wavelengths so enormous that their individual energies are essentially negligible. Neutrinos, nearly massless particles that interact only weakly with matter, will drift through the expanding space in vast numbers, cooling toward equilibrium with everything else. If protons have not decayed, electrons and protons will still exist, though in such low densities across such enormous volumes that the chance of any two of them interacting becomes vanishingly small. If protons have decayed, the matter content will be even more sparse, primarily electrons, positrons, photons, and neutrinos, along with whatever exotic stable particles the full theory of physics permits. The expansion of the universe will continue throughout all of this. Space itself will keep growing, driven by dark energy, carrying whatever particles remain further and further apart. The average distance between any two particles will increase without limit. The universe will become not only cold and dark but unimaginably sparse, a near-perfect vacuum stretching across distances so vast that the concept of distance itself becomes almost meaningless. Whatever structure remains will be the quantum fluctuations of the fields that permeate space. Tiny, random variations with no pattern, no organization, and no ability to produce anything more complex than themselves. This is the heat death. Not an explosion, not a collapse, not a dramatic finale of any kind. It is an arrival at the state of maximum entropy, a condition of perfect, featureless equilibrium from which no further change can emerge. It is the universe having thoroughly and completely used up every gradient, every difference, every source of order that the Big Bang introduced into existence. The low entropy state of the early universe, that highly ordered, energetic, densely packed beginning, has been the source of everything that has happened since. Every star, every planet, every galaxy, every living thing has been, in a thermodynamic sense, a consequence of the universe spending down that initial endowment of low entropy. And when it is fully spent, there is nothing left to spend. There is a philosophical dimension to the heat death that is worth sitting with quietly for a moment. The second law of thermodynamics gives the universe a direction. Time, in a thermodynamic sense, flows from low entropy to high entropy, from order toward disorder, from concentration toward dispersal, from difference toward sameness. The heat death is the endpoint of that direction, the place the arrow of time has always been pointing. In that sense, the heat death is not something that happens to the universe from outside. It is the natural conclusion of processes that have been running since the very beginning, the inevitable destination of a journey that started with the Big Bang and has been moving through every star and galaxy and moment of complexity along the way, toward this final, quiet, permanent equilibrium. There is something deeply restful about that picture, if you allow yourself to consider it without alarm. The universe is not heading toward chaos in any dramatic sense. It is heading toward stillness, toward a state in which nothing disturbs anything else, in which every gradient has been smoothed away, in which the long work of entropy has been fully and finally completed. It is the universe at rest, in the most complete and permanent sense of that word. Nothing will ever disturb that rest. Nothing will ever introduce a new source of order or difference into a universe that has reached maximum entropy. The stillness will be total, and it will last forever. Chapter 8. What darkness actually means. Throughout this journey, we have been moving toward darkness, using the word as a destination, as a description of the universe's eventual state, as the natural endpoint of a long process of cooling and fading and entropy. But darkness, as a concept, deserves more careful attention than it typically receives. It is not simply the absence of light in the way that an unlit room is dark. The darkness the universe is moving toward is something more complete and more fundamental than anything we encounter in ordinary experience. And understanding what it actually means, physically, philosophically, and in terms of what it implies about the nature of existence, is worth exploring with the same patience we have brought to everything else tonight. In everyday experience, darkness is relative and temporary. A room is dark because the light has been turned off, but the potential for light remains. The bulb is still there, the electricity is available, the atoms in the air are ready to be excited and emit photons if energy is applied. The darkness of a moonless night is darker, but the sun is still shining on the other side of the earth, and in a few hours the light will return. Even the darkness of deep space, as experienced by an astronaut far from any star, is not complete. Photons from distant stars and galaxies are passing through that space in every direction. The cosmic microwave background radiation fills every cubic centimeter of the universe with its faint warmth, and the potential for light remains everywhere that matter and energy exist. The darkness of the universe's final state is categorically different from all of these. It is not the absence of light in a space where light could still exist if conditions were right. It is the absence of any process capable of producing light in a universe where the conditions for such processes have been permanently and completely exhausted. There is no fuel left to burn. There are no temperature differences left to drive radiation. There are no excited atoms waiting to release their energy as photons. There is only the thin, cold, expanding remnant of a universe that has fully spent its initial endowment of order and energy, settled into perfect equilibrium, with nothing left to disturb it. This distinction matters because it speaks to something deeper than the mere absence of photons. Light, in physics, is a consequence of change, of electrons moving between energy levels, of charged particles accelerating, of hot matter radiating according to its temperature. Where there is change, there can be light. The final darkness of the universe is not simply a place where change is not currently happening. It is a state where change cannot happen, where the conditions that would allow any process to occur no longer exist. It is darkness as a permanent physical state rather than a temporary circumstance, and that permanence is what makes it categorically unlike any darkness we have ever experienced or can directly imagine. There is a related concept worth considering here, which is the nature of cold in the universe's final state. We tend to think of cold as the absence of heat, the way we think of darkness as the absence of light. But in thermodynamics, cold has a more specific meaning. It refers to the state of a system with low thermal energy, where the random motions of particles are slow and the capacity for those motions to drive useful processes is limited. The cold of the universe's final state is not simply low temperature in the way that winter is cold, or the surface of a distant planet is cold. It is a temperature so close to absolute zero, across a volume so vast, that the thermal energy per unit volume approaches zero in any practical sense. There is no warmth left anywhere, not because warmth has been removed, but because it has been perfectly distributed, spread so evenly across such an enormous volume that no region has more than any other, and the universal average is essentially nothing. Darkness and cold together define the final state of the universe in a way that is more than merely descriptive. They are expressions of the same underlying physical reality, a universe that has reached maximum entropy, in which every gradient has been eliminated, every difference smoothed away, every source of order and energy fully and finally spent. The darkness is not an accident or a side effect. It is the direct physical consequence of a universe that has completed its thermodynamic journey. The light was always temporary, a product of the low entropy conditions that existed at the beginning and have been declining ever since. The darkness is what was always waiting at the end of that decline. It is natural, when contemplating this picture, to ask whether the darkness is truly final, whether some process, some fluctuation, some event could disturb the equilibrium and introduce new order into the universe. The answer that physics currently offers is nuanced. In a universe at maximum entropy, quantum fluctuations will still occur. The fields that permeate space will still undergo the random variations that quantum mechanics requires, and over timescales so vast that they make even the black hole era seem brief. These fluctuations could in principle produce, purely by chance, a spontaneous reduction in local entropy, a random assembly of particles into some more ordered configuration. This idea is associated with the concept of a Boltzmann brain, a hypothetical self-aware structure that could arise through random quantum fluctuation in a universe at maximum entropy, existing briefly before dissolving back into equilibrium. The timescales involved in such fluctuations are staggering even by the standards of everything we have discussed tonight. A fluctuation large enough to produce something as ordered as a single protein molecule would require a waiting time so immense that the entire history of the universe to the heat death would not register as a measurable fraction of it. A fluctuation large enough to produce a functioning brain, or a planet, or a star, would require waiting times that are essentially infinite in any practical sense. These fluctuations are permitted by the mathematics of statistical mechanics, but they are so improbable that their occurrence in any finite span of time cannot be meaningfully distinguished from impossibility. What this means is that the darkness of the universe's final state is, for all practical and philosophical purposes, permanent. The equilibrium once reached will not be spontaneously broken on any timescale that has meaning. The universe will not restart. It will not generate new stars from the remnants of the old ones. It will not find a way back to the low entropy conditions of the Big Bang. It will simply persist, cold, dark, still, and expanding, for a duration that has no upper limit and no foreseeable end. And yet, there is something in this picture that is not entirely bleak if you approach it from the right angle. The darkness of the universe's final state is the direct consequence of everything that came before it. The light that stars produced, the complexity that galaxies built, the warmth that planetary systems sustained across billions of years, all of it contributed to the entropy that eventually leads to equilibrium. The darkness is, in a sense, the record of all the light that ever was. Every photon that ever left a star and traveled through space, every reaction that ever drove a living process, every moment of warmth and illumination across the entire history of the cosmos, all of it is encoded in the final state of the universe as the entropy that process produced. The darkness does not erase what came before. It is what came before, fully spent and fully accounted for, resting in the only state that the laws of physics allow after everything else has run its course. Chapter 9. Alternative Endings. Everything we have explored so far has followed a particular trajectory. The slow, patient arc from the age of stars through the Degenerate Era, through the evaporation of black holes, and into the final equilibrium of heat death. This trajectory is grounded in our current best understanding of cosmology and physics, and it represents what many scientists consider the most likely long-term fate of the universe, given the evidence available to us today. But science is honest about the limits of its knowledge, and the honest truth is that the ultimate fate of the universe is not known with certainty. There are other possibilities, other endings that the physics of the universe might be pointing toward, depending on factors we do not yet fully understand. Some of these alternatives are dramatic, some are subtle. All of them are worth considering with the same calm attention we have brought to the heat death scenario, because they illuminate different aspects of what the universe is and what its future might hold. The first, and perhaps most dramatic alternative ending, is known as the Big Rip. It arises from the behavior of dark energy, the mysterious component of the universe that is currently causing the expansion of space to accelerate. In the standard cosmological model, dark energy is treated as a constant, a fixed energy density associated with empty space that does not change over time. This is consistent with current observations and leads to the gradual endless acceleration of expansion that eventually results in the heat death scenario. But dark energy is not well understood at a fundamental level, and there are theoretical models in which its strength is not constant, but increases over time. If dark energy grows stronger as the universe ages, the consequences become increasingly dramatic. In such a scenario, the accelerating expansion would eventually become so intense that it would overcome not just the gravitational bonds holding galaxy clusters together, but the gravity holding individual galaxies together, then the gravity holding solar systems together, then the electromagnetic forces holding planets and rocks and molecules together, and finally even the forces holding atomic nuclei together. In the final moments of this scenario, the fabric of space would be expanding so rapidly that every structure in the universe, down to the subatomic level, would be torn apart by the expansion itself. This event, the Big Rip, would represent a genuinely catastrophic end to the universe, occurring in finite time rather than the infinite slow fade of heat death. Current observations do not strongly favor this scenario, but they do not rule it out entirely, and the question of dark energy's true nature remains one of the most significant open problems in all of cosmology. A second alternative is the Big Crunch. In the early decades of cosmological thinking, before the discovery of the accelerating expansion of the universe in the late 1990s, the Big Crunch was considered a plausible fate. In this scenario, the expansion of the universe eventually slows, halts, and reverses under the influence of gravity, causing the universe to collapse back in on itself in a mirror image of the Big Bang. Temperatures and densities would rise as the collapse proceeded, and the universe would end in a state of extreme heat and density, the opposite of the cold darkness of heat death. The discovery of dark energy and the accelerating expansion has made the Big Crunch appear very unlikely in the context of our current understanding. but it remains a theoretical possibility if the nature of dark energy changes dramatically in the future in ways that our current models do not anticipate. A third possibility is something called the Big Bounce, a variation on the Big Crunch in which the collapsing universe does not end in a final singularity, but instead reaches a minimum size and then rebounds into a new expansion. In this scenario, the universe is cyclical. It expands, contracts, bounces, and expands again, potentially repeating this cycle indefinitely. Some versions of loop quantum cosmology, a theoretical framework that attempts to apply quantum mechanics to the structure of space-time itself, suggest that the Big Bang may itself have been such a bounce, the rebound from a previous contraction. If this is the case, our universe may be one episode in an infinite series of expansions and contractions, each one a universe in its own right, connected to the others through the quantum geometry of space-time. This is a speculative idea, and the evidence for or against it is currently limited, but it offers a picture of cosmic existence that is neither a beginning nor an end, but an endless cycling through states of expansion and contraction. Another alternative that has received serious attention is the possibility of vacuum decay. In quantum field theory, the state of lowest energy for a quantum field, called the vacuum state, may not be the true lowest energy state possible. If the current vacuum state of the universe is what physicists call a false vacuum, a locally stable but not globally stable configuration, then there is a possibility, however small, that a quantum fluctuation could trigger a transition to the true vacuum state. This transition would propagate outward at the speed of light as a bubble of true vacuum expanding through the false vacuum of our universe. Inside the bubble, the fundamental constants of physics and the nature of matter itself would be different, and almost certainly incompatible with the existence of atoms, stars, planets, or any form of structure as we know it. The bubble wall, traveling at the speed of light, would be undetectable in advance from any location it had not yet reached. There would be no warning. The universe would simply be one thing, and then, as the bubble wall passed through, it would be something else entirely, something in which the structures of our universe could not exist. Vacuum decay is an unsettling prospect, but it is worth noting several things about it. First, there is currently no evidence that we live in a false vacuum, though some calculations based on the measured mass of the Higgs boson suggest that our vacuum may be metastable, stable enough to persist for an extremely long time, but not necessarily forever. Second, the timescale for vacuum decay, if it occurs at all, is estimated to be extraordinarily long, likely far longer than the timescale for heat death. Third, and perhaps most relevant to the spirit of tonight's exploration, vacuum decay would not be experienced as a catastrophe by anyone within the bubble's path. It would simply happen, instantaneously and without warning, and there would be no experience of it at all. It is an ending that, if it occurs without witnesses. There is also the possibility that the universe's fate depends on aspects of physics that we have not yet discovered. Our current understanding of cosmology is built on general relativity, quantum mechanics, and the standard model of particle physics, frameworks that have been extraordinarily successful in describing the universe across a vast range of scales and conditions, but which are known to be incomplete. General relativity and quantum mechanics are not yet reconciled into a single consistent theory of quantum gravity, and there are phenomena, dark matter, dark energy, the matter-antimatter asymmetry of the universe, that our current frameworks describe but do not fully explain. A more complete theory of physics might reveal new processes, new forces, or new properties of space and time that alter the long-term trajectory of the universe in ways we cannot currently anticipate. This uncertainty is not a weakness of science. It is an honest acknowledgement of where the frontier of knowledge currently stands. Science does not claim to know everything. It claims to know what the evidence currently supports, and to be honest about where the evidence runs out. The heat-death scenario is the best current answer to the question of how the universe will end, but it is an answer that holds its conclusions with appropriate humility, aware that new discoveries could revise the picture in significant ways. The universe has surprised us before. The discovery of the accelerating expansion was one of the most unexpected results in the history of cosmology, and it may surprise us again. What all of these alternative endings share, regardless of their specific mechanisms and timescales, is that they point toward the same fundamental truth that the heat-death scenario also expresses: that the universe is not static, not permanent, and not without direction. It began in a state of extraordinary order and energy, and it is moving, through processes we can observe and measure and calculate, towards some final state that represents the exhaustion or transformation of that initial endowment. Whether that final state is the cold equilibrium of heat-death, the violent dissolution of the Big Rip, the cyclical renewal of the Big Bounce, or something our physics has not yet imagined, the universe has a story with an arc. And we, in this present moment, are living somewhere in the middle of that arc, in the warm, luminous, complex middle chapter of a story that began long before us and will continue, in one form or another, long after everything we know has changed beyond recognition. Chapter 10. Resting in the dark. We have travelled a long way tonight. We began in the warm, luminous present, a universe alive with the light of trillions of stars, still young by cosmic standards, still forming new suns in distant clouds of gas and dust. We moved through the long twilight of the red dwarfs, through the cold patience of the Degenerate Era, through the slow evaporation of the last black holes, and into the final stillness of maximum entropy. We considered alternative endings, the violence of the Big Rip, the cyclical renewal of the Big Bounce, the quiet, instantaneous transformation of vacuum decay. And through all of it, we have been moving toward a single, quiet conclusion: that the universe, given enough time, tends toward darkness, not as a punishment or a tragedy, but as the natural and inevitable consequence of the laws that have governed everything from the very beginning. It is worth pausing here near the end of this long journey to ask what we are supposed to feel about all of this. It is a question that cosmology does not answer directly. Science describes what is and what will be, but the meaning we make of those descriptions is something we bring to them ourselves. And the meaning that this particular description invites, if you sit with it quietly and without resistance, is something that feels less like despair and more like a kind of deep, settled peace. The universe ending in darkness is not a story about loss, or not only that, it is a story about completion. Every process the universe contains is, in thermodynamic terms, a spending down of the low entropy conditions that the Big Bang established. Every star that has ever burned, every planet that has ever warmed in the light of its sun, every moment of complexity and organization and life that has ever existed anywhere in the cosmos, all of it has been part of that spending. The darkness at the end is not the negation of all that came before. It is the record of it. It is the universe having fully expressed everything that its initial conditions made possible, having run every process to its conclusion, having left nothing unfinished. There is a kind of completeness to that picture that is, if you allow it to be, genuinely restful. there is also something worth noting about our position in this story. We exist in what may be, from a certain perspective, the most interesting era the universe will ever know. The Stelliferous Era, the Age of Stars, is the only period in cosmic history during which the conditions for complexity, chemistry, and life as we understand it can exist. The Degenerate Era that follows will be vast beyond description, but it will be quiet and dark and essentially featureless by comparison. The Black Hole Era will be vaster still and even quieter, and the heat death that follows will make all of those eras seem eventful. We are not living in a late or diminished chapter of the universe's story. We are living in its most luminous and dynamic period, a brief, warm, extraordinarily rich moment in the middle of an otherwise almost entirely dark cosmic history. That perspective does not make the eventual darkness less real or less final, but it does change the emotional register in which we hold it. The darkness is coming, yes, but it is coming after an unimaginable abundance of light. It is coming after trillions of stars have burned across billions of years, after galaxies have formed and merged and slowly faded, after every process that physics permits has run its course with complete thoroughness. The darkness is not premature. It is not cruel. It is simply what comes after everything else has had its full and complete expression. There is a particular quality to the night sky that becomes more meaningful in this context. When we look up at the stars, we are not looking at permanent fixtures. We are looking at ongoing processes: hydrogen burning, gravity balancing radiation pressure, nuclear reactions producing the photons that travel across space to reach our eyes. Each of those stars is a temporary structure, a brief organization of matter and energy that will eventually run its course and leave behind a cold remnant. The light reaching us from even the nearest stars is the product of processes that have been running for millions or billions of years and will eventually end. In that sense, every point of light in the night sky is a small argument against permanence, a reminder that the luminous universe we inhabit is a feature of a particular era, not a fixed and eternal condition. And yet that impermanence does not diminish the light. If anything, it deepens it. The stars are burning because the conditions for burning exist right now, in this era, in this chapter of cosmic history. The warmth of the sun on a clear day, the faint glow of distant galaxies in a long exposure photograph, the quiet light of a single star on a dark night. All of these are expressions of processes that are genuinely remarkable, genuinely rare in the full sweep of cosmic time, and genuinely finite. They will not last forever, but they are here now, fully present, doing what the physics of this era allows them to do. The universe moving toward darkness is, in one reading, the universe moving toward rest. Every process, every gradient, every temperature difference, every organized structure is a kind of tension, a departure from the equilibrium that entropy is always seeking. The stars are tension. The galaxies are tension. Life is tension, extraordinarily complex, extraordinarily organized, extraordinarily far from equilibrium. And the universe, patiently and thoroughly, is always working to resolve that tension, to smooth away the differences, to bring everything toward the stillness of maximum entropy. The darkness is not the universe failing. It is the universe succeeding, in the only direction that the second law of thermodynamics allows. There is nothing to be anxious about in that picture. The timescales involved are so immense that they place the eventual darkness in a category entirely separate from anything that touches human experience or even human imagination in any practical sense. The sun will continue burning for another 5 billion years, The last red dwarfs will burn for trillions of years beyond that. The Degenerate Era will stretch for timescales that make a trillion years look like an instant. The darkness, when it finally arrives, will arrive after a duration of cosmic activity so vast and so thorough that the word enough, rarely applicable to anything, seems genuinely appropriate. The universe will have had enough time to do everything it was capable of doing, and then it will rest. Tonight, wherever you are, the stars are still burning. The universe is still in its luminous era, still producing light on a scale that is almost impossible to comprehend, still running the processes that make complexity and warmth and the quiet contemplation of a night sky possible. The darkness that eventually comes is real, and it is final, and it is written into the physics of the cosmos as surely as anything we know. But it is also extraordinarily far away, separated from this present moment by a span of time so vast that the entire history of the universe to date would not register as a meaningful fraction of it. For now, there is only this: the quiet night, the steady light of distant stars, and the deep, unhurried patience of a universe that has nowhere it needs to be. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.